All right, this one says aspirin acetyl salicylic acid. That means this one is a organic compound that is it's like in a cyclic form, like a benzene, cycloalkane, things like that. It's prepared by heating salicylic acid, which is this. This is an acid with acetic anhydride, which is that one there. The other product is acetic acid. All right.
Okay.
So,
like acid.
yeah, they're basically all like acids. So here, they say, what is the theoretical yield? You say they want it in grams. That's why you were saying, when you were saying theoretical mass, it doesn't have to it doesn't have to be mass. It can be length, can be distance, can be moles. Everything is theoretical we have ever learned in school. Yeah, but they just prefer you calculating mass of aspirin for this. We want that guy. 984. Let's go check what is 984. 984 is this one in a green box. Let's see which one is given. And then they say when 200 grams of salicylic acid is heated. All right, we've got 2 grams of, remember this one, the one with the 7. So this one, it's 2 grams. We got 2.00 gram of that one is given. Okay, now, and also 4 grams of acetic anhydride, 4 grams. We also have to do 4 grams of that one. So if they want us to calculate the mass of that, of which we are going to do, it's going to be called theoretically. Hence, there must be an actual mass of this one given. So when you go further, it says the actual mass of aspirin is 1.86 gram. What is the percentage yield? Or let's write it, what is the actual percentage yield? You see, that one we don't need it, 1.8. We'll need it later when you're doing the percentages. Are we together on this one, right?
Yeah.
Okay. Now, last time what I did, you were supposed to have one number to work with, and then you basically done. But we know in chemistry, once we're given 2 quantities, quantities of 2 different substances, we need to check which one is a limiting reactant, and then we actually use that one. So must I use 4 to get the mass of the green box? Or should I use 2 to get the mass of the green box? That's what we need to do first. So, yeah, so first, I'm going to calculate the moles of this one here. So the number of moles, it's actually the mass, which is 2 divided by. All right, so we already know that carbon is 12. We did that, so it's 12 times 7. Then we're going to plus it with oxygen is 6 times 1, which is 6 plus 3. I meant hydrogen rather. 3 times 16 for the oxygen. 138. So it's 2 divided by 138. All right, so that means I can now type 2 divided by 138, because in the chemical equation, we only work in relation with moles. So there's the value there. So I've got 0.01. Well, I'm going to go 3 significant. I'm going to go 4, 5. 4, 5 there. Those are moles in green.
Yeah.
I must also do for this one, yeah. This one, yeah. It's going to be 4 divided by whatever. All right, so this one again, the number of moles is going to be 4 divided by relative molar mass. So let's get the relative molar mass. Carbon is 12, but we're going to times that by 4. Hydrogen is 6 plus 3 times 16 for the oxygen. 102. So I've got 4 divided by 102. Actually, which will be done if we're given one quantity. But they just want us to give us extra work. So it's 0.0392. I'm going through significant figures. So now we've got the moles. I don't need the red numbers. If the equations are balanced, of which I believe there are, carbon is 7 plus a 4, that will make it 11. 9 plus 2, it's 11. Hydrogen is 6 and 6, which is 12. 8 plus that one is 12. Oxygen is 6. 4, yeah, it's balanced.
Yeah.
So which means if we do, yes, sir.
Oh no, sorry. Sorry, I didn't mean to.
All right, since the ratio are the same for these two, 1 is to 1. I don't need to compare them. The one that has the smaller moles is the one to go for. We good?
Okay.
Yeah.
So why are we using? Yeah.
Why
are we using the smallest one, with the smallest mole?
Remember, the limiting reactant is the one that will be used up, all of it.
Oh yeah, yeah. Okay.
Yeah. So what I'm saying is this. I want you to look at this equation. Mathematically speaking, we've got 4 terms. There are 2 terms here on the left, 2 terms on the right, isn't it?
Yeah.
Mathematically speaking. Or we can say we've got 4 compounds, 2 compounds on the left, 2 compounds on the right. Yeah. So in chemistry, you must give me information regarding only one term, one compound. Let's say, for example, this was not there. You have no doubt you must use that green number for the rest of every calculation.
Yeah.
Is that making sense?
Yeah.
Yeah. But once you're given 2, now you're like, which one do I use to calculate the rest? Do I use the first number or the second? Yeah. That's why you have to eliminate one of them. That's why limiting reactant comes in. Yeah, it's a way of eliminating. One of the number must not be used here. You have to pick one. And the one that you pick, it's not just any. It must be the correct one. Now, the question is, how do I know which one is the correct one? The one that runs out first. Yeah. Limiting reactant, yeah. Yeah. All right. So the small, it's because of the ratio. It's because I told you it's 1 is to 1. Yeah. Like, let's get rid of this now. If I were to use 0.0145, how much will I ask for from this one? According to the ratio, I'll ask for the very same amount. This one that I cancel, it should provide me with 0.0145. Then I check if it has. Does it have that amount? Does it have that amount? Yes, it does, because it has it has plenty. So the one that has plenty, it's not the one that we use for calculation. Then I figure out that no, you are the rich boy. That's what I said yesterday. We use the poor one, the little one. Yeah. You see? Or vice versa, if we're to use 0.0392, how much will it ask for from the other side? It will ask the same amount, 0.03392. Then I check that one. Does it have enough? It says, no, I'm sorry, I don't have enough. We said, you are the one who's limiting us. We cannot go further. We cannot react any further because you don't have enough. Okay. So for us to be able to react, that means every one of us must come to your level. So that's how we use that one. We go to its level. Do you understand what I'm saying? Yeah. So that one is out. We don't need it. So we use 0.0145 to get the moles of this one. So the ratio is still 1 is to 1. So the ratio will be the same. So that means it's also going to moles. But we want to convert that to grams. How do we get grams? The mass, it's given by the number of moles multiplied by the relative molar mass. So it's going to be 0.0145 multiplied by, let's do relative molecular mass for that one. There are 9 carbons, meaning 9 times the 12. Then I must plus it with 8 from the hydrogen, plus 4 times the 16. 180. So we times it by 180, it will give the gram. Normally speaking, if these guys have 1.86, can you see 1.86? Our answer shouldn't be too far from that. It should be somewhere close. Somewhere close. Yeah. Because there is somewhere close to that one there. All right, so let's see. I already have the 180. I'll go ahead and times it by 0,0145. Yeah, it's about 2. You see, we've got 2,61 grams. This is theoretical mass because it's in gram. That's why we're calling it mass. Theoretical mass. Yeah. The reason why theoretically it's perfect compared to the reality. I'm not saying it's a perfect answer. I'm not saying it's a real answer. I'm saying, okay, let's say right now I ask you to take a clay. You know clay?
Yeah.
The one you use to mold some stuff, a clay.
Yeah.
Or we can say a dough. It doesn't matter. And I say, I want you to make a perfect sphere in your mind with clay, an imaginary clay. With an imaginary clay in your mind, you can make a sphere which is perfect. You can imagine perfectly, correct?
Yeah.
But if I say mold it physically, make a perfect, you can't. Physically, though it is the truth, but it's not up to perfection because there are errors in a physics. Right now, I can say, I want you to fly from here to America. In your imagination, you can fly perfectly.
Yeah.
But then I say, do it now physical. You can't.
Yeah.
Did you understand what I meant by that now? Is it making sense?
Yeah.
Yeah. It's because in a physical, if you are going to measure the mass on that scale, maybe there's some particles of dust also you are measuring also. You don't know the actual mass. But anyway. So let's do percentage. The actual percentage is going to be 1,86. The actual number divided by 2,61. And we times it by the 100%. So there is still another one more question on this one, just as a bonus. Divided by 2,61. So the only thing that whenever you see that you are given, say it's 71%, so 71,3%. Whenever you're given two quantities of different molecules, you know you must do limiting reactant. The one I have to tell you necessarily. Okay, here's the last one. Here's another one, last one. Methyl salicylate oil of wintergreen is prepared by heating a salicylic acid, which is this one, with methanol, that one there. There's the equation there. Now they tell me in an experiment, 1.5 gram of salicylic acid, which means this one, the first one. So they're giving me the grams, it's 1.50 gram. And then it's heated with 11.2 gram of methanol, that one there. So the gram here is 11.20. The reason why I wanted to do the second one, it's because these ones, they are involving limiting reactants. I did it on purpose to kind of help you remember, also to recap on that one. The yield of the methyl salicylate, that one, is this much. You see, the yield. Now, wait a minute. Because they've been talking about percentage yield. What was that yield? Like I told you, I called it the actual percentage yield. Do you understand what I'm saying?
Yeah.
Yeah. So they didn't even use the word actual. This is the actual amount. So sometimes you're like, how do I get the clue whether this is actual or theoretical? So this is you see, it's the yield. So call it actual percentage yield. Actual percentage yield. So this is the actual amount, that one. This is the actual. So we ignore it. We do our own calculation and compare it to the reality. All right, I believe this equation is balanced. I've got 7 carbon, 8, it's 8. Hydrogen, 6. and a 6 and a 4, 10, 8, 2, 10. Oxygen, 3 and 1, 4. Yeah, it is balanced. So the ratios are all 1:1, all 1:1. So it's good. All right, so I need to know for the calculations of this one. Let's put it in a box already. To get the mass of the one in a green box, which one do I use? Do I use the one that has a 1.5 or the one 11.10? First, I need to change them to moles and check which one is the smallest, because the ratio is 1:1. The one that comes out to be small will be the one. All right, so yeah, you see, one of them must be eliminated. So we're having n equals to 1.50, and then we're going to divide that by a certain number. So I'm dealing with the first one. Carbon, we know it's 14, it's 12, 7 times 12. And then plus hydrogen, 6, plus 48, which is basically 3 times 16. I know it's 48. That's the number, 138. So we're dividing this by 138. All right, so 1.5 divided by 138, and then we get that. Okay, I'm gonna go 3 significant figures. So we've got 0,0109. That's the mole, the green one. Let's do the next one. So the next one, it's also gonna be the number of moles. It's actually 11,20 divided by, let's work out the next one. So the next one with carbon is 12. When I look at the hydrogens, they're basically 4. So plus the 4, oxygen is just 16. No. Okay, I'll keep it as times 1. I almost make a mistake. It doesn't alter anything. Plus 16 is 32. So I must take 11.2 divided by 32. It will give me the moles. The moles that I have now, I'm having, let's do this. I've got 0,35. So since this 1:1, the green has the smaller amount. Can you see that?
Yeah.
Yeah, so we use the green to get that. So this one will have the same amount of moles as that green number. So we just need to get the mass. So we can just write it and say the mass of that one, because it's like on a standby. The mass is gonna be 0,0109 times by relative molecular mass. We got carbon is 12, 8 times 12, and then plus hydrogen is 8 plus 48, which is basically 3 times 16, 152. So we're going to times that by 152. Let's see how much we're getting. So 152 times 0,0109. Not far, 1,65. So it's 1,6. Let's make it 7. No, 6 grams there. This is the theoretical. So when they want the actual percentage yield, so we take the actual number 1.27 over the theoretical 1,66. We times it by 100, and then we'll put the percentage symbol. So I've got 1.27 all over 1,66 times by 100. So you see what when we're doing this thing, what is it? Why do we have to calculate this? This is simply telling us how close were we to the real answer, to the actual value. You understand what I'm saying? Yeah. So that means we were like 77%. So if I take 100, I don't know if it's 33 or 23 minus, I'm just going to say minus 77. We were off by 23%. So the 23% is the impurity part. Can you see? Yeah. So there we were. So this one, I hope it's done. I think you're okay with